Hello, everybody. Go ahead and get started here, I think. Yeah, so this is my talk on extending Zephyr at runtime. Many of you probably know me, but if not, I'm Tom Burdick. I work at Intel Corporation. So what is LLEXT? And I'm going to name it. I know it's an acronym. It is an acronym, Linkable Loadable Extensions. But when you look at the name, I want you to think about Lloyd the Llama from Wikipedia and all the double L's that come along with it. We were having a great talk yesterday about what is a Zephyr subsystem. Well, LLEXT is a Zephyr subsystem, and there's many of those. But it's also an ELF loader, also another fun acronym, executable and linkable format. But maybe another kind of way to put it is it's a toolbox to build and manage and load ELFs in a particular way. What's an ELF? I mean, I think a lot of us know, but this is a kind of a fun graphic. It's a file format. We've got headers, sections, section headers. But kind of some key elements in this are, we have blocks of code, instructions, ARM instructions, extends instructions, x86 instructions, whatever target we're building for. We've got data. Some of it's, constant data, constant string. Some of it's read-write data. Some of it's, the better saved space data, right, where it just expands at runtime and uninitialized. So kind of going back to what is LLEXT, right? It's an extension manager. And so, to manage these loadable runtime extensions, we need to have something. We have a couple of nice functions to do that, load and unload. Finding symbols in our ELFs. We keep a list of these extensions in memory and some sort of like key structure elements here that we want to kind of keep in mind as part of what we're doing and managing these things. We have a name and a use count. Interesting. But there's some other fun members in here that we're going to get to. So LLEXT is also a memory manager. Memory is actually really important for these extensions, as it turns out. And it has a dedicated heap. We have, read-write memory. We have executable memory. And these things all kind of need to be set up in a way where, we can actually go run things that we want to run the way we want to run them. So in order to do that, we need to kind of set, all right, we have our .text section in our ELF. We have our data section. Text is, full of executable code. By default, when we load Zephyr, only our initial .text is executable. So we need to do something there, possibly. We need to kind of like copy our data, our initialized data into read-write memory, so we can actually use it. We need to expand out our better save space, description in our ELF. It's not actually in there. We just have a section size and our read-only data. So, right, when we load all this stuff up initially in Zephyr, there's kind of two options that we can do. Today, we can either enable, if we have our MPU or MMU enabled, we need user space enabled. Or we can just not use any sort of hardware memory protection. The big part of that is, okay, well, if we would like to actually execute code in an extension and jump to a random address, basically we just load our ELF file, we copy things in, maybe somewhere in there, and I say, oh, jump to my hello world function. What's going to happen by default is there's going to be an exception because that part of memory is not executable. So we can deal with that by either, again, disabling memory protection entirely or enabling user space and doing a lot of what Daniel was talking about in his last talk. If you were here for user space, by setting up memory partitions in a memory domain. And part of that is you do get the option to set up memory permissions in terms of like read, write, and execute. So there's different ways we can execute that code in an extension. I mean, it's random code. Maybe we picked it up off the internet. Hopefully not. But you know, if we don't have, if we want to run things in kernel space, any thread can call in there. Again, you know, assuming that you've either disabled your memory protection hardware or you've enabled user space. Even if your thread is in kernel space, you still need to use user space to be able to manipulate those memory permissions and set up those memory regions or pages. Yeah, and so in user space execution, this is kind of interesting. You know, like let's say we want to try and sandbox our extension that we've loaded. So we do have, you know, our MPU enabled or our MMU enabled. And in a way, you know, we're kind of creating a process, kind of like a Unix process. We can't touch, you know, our kernel memory at all. We can run code, but we can't actually touch any kernel data. But we can still run, you know, all the new things that we've just loaded in, our data, our better safe space, our BSS, our RO data, our text, which is quite nice. So we've sort of, again, created a process. So what else is LLEXT, or LEXT? It's also a symbolic linker. And this is kind of key to actually making everything work. The base firmware has, you know, uses a macro called export symbol. And if you've seen the Linux version of this, it's very similar. Creates a section in your linker script with a sorted array of names and address pairs. And extensions can do the same thing in themselves with a slightly different macro today, LL extension symbol. And so why do we need all of this stuff, right? I mean, it seems like, you know, we have to manage memory. We have to keep track of a mapping of names to names to addresses. And really this all comes down to, this is all needed just to simply get to hello world. And that is because ELFs have relocations. And these relocations allow you to place that .text anywhere in memory, in our case, right? So you can load your .text anywhere that you've allocated it. But to be able to do that, you know, your executable code needs to know where to find things. Find variables, let's say in your .data or RO data section, find functions that haven't yet been defined in itself. So we get relocations like this when we see our sort of basic hello world extension. We have, you know, an RO data address to the string that we want to print. And we have you know, an undefined reference to a symbol, print K. So when we actually go to load this extension, we need to look at this ELF and see these relocations and rewrite them with the actual address of these things, right? Either objects in memory or symbolic references to functions. So what are some key points about these relocations? The kinds of relocations that are going to show up are architecture dependent. As we kind of saw here, this is specific to ARM, but there's actually, you know, relocations specific to each architecture. And it also depends on the ELF linkage. So as you're compiling, you know, you can have flags to create relocatable objects, which typically you don't see when you're compiling your normal C program. Those all get linked together. But we actually end up using them in LEXT, or static or shared. Also depends on, you know, sometimes your compiler flags can change, you know, what kind of relocations show up, as Luca helped solve an early issue that we ran into, right, where there was a kind of a tricky relocation to do that I didn't really want to deal with right away to get to hello world, and this great compiler flag in long calls, so you only get absolute address trumps, which is made things quite a bit easier. And that kind of gets into the next point here, where these relocations do require, at times, you know, it's not always simply like, hey, I have an address, my string is over here. A lot of times they are instructions, instructions for moves, instructions for loads, instructions for branch and links. And those instructions are encoded in a particular way for that particular architecture. So in order to update them with the appropriate address, you have to decode that particular architecture's opcode, change a part of it, and then re-encode it, which I think Cedric did a great job adding many of the ARM ones, which is very, very quite nice. So, and some of these jump codes, some of these opcodes require PC relative addressing. So, if we kind of look at some function call that might be in your extension, going from one function to another, a lot of times these are program counter dependent to keep them small. So you don't always have to store a 32-bit address right in your instruction. So if you're using ARM thumb or extensa, right, you have a 16-bit opcode perhaps. You only get so many bits to store an address relative to your PC. And that, again, makes it a little trickier to do. If you can imagine for a moment, if that address to that function is too far away for that particular opcode to represent, now you need to create a jump table. And that's exactly why the imlong call kind of saved the day initially, right? I didn't want to have to go create a jump table. Yeah, so kind of continue on with some key points about relocations here. These sections can be very interdependent. Text obviously needs data. Your instructions obviously need data. But data can actually need other data as well. And so each section that you have in your ELF file has an associated section typically with these relocation instructions associated with it. Symbolic linking at the moment, kind of requires like finding print K. We have a table, it's sorted, but today it is a linear search of string comparisons, which can take some time. I think as Cedric noted in his talk, it took quite some time to load some of the ELFs. So this is maybe one of these cases where we could do a better job in the future. So loading an ELF at a high level, what does this actually mean? Well, we read the ELF file, we check out the headers, we look at the sections, maybe we copy some of them, maybe we reference some of them. Relocations are applied, those instructions are applied to rewrite opcodes or rewrite addresses, so everything looks pretty and it looks as if we knew where everything was to begin with, although we didn't. And finally, the extension is added to a global list, and at long last, symbols in our extension, functions, objects, can finally be referenced. We can use them, we can call into them, we can look at them. So how do we actually build one of these? Kind of a great, a quick little sample here. When I started first doing this, it was very nice to just be able to call the compiler directly and do object dumps and kind of see all of this ELF data. So I think it's still quite nice to be able to do this manually. Again, to sort of experiment and tinker, and as you're looking, at least as I was looking at these relocations and trying to understand it all better, this was a quick and easy way to do it without having to involve all of CMake. But since then, Luca has done a great job adding some CMake functions that make all of this very, very simple. Looks pretty much just like adding a library target in Zephyr. And you can give it a name, sources, output, easy. I kind of want to give one more, let's take this to the next level though, and talk about this great PR by Ederson, adding an EDK. So let's say we want to go a step further with our extensions. We don't want to just build them in the same tree as our application. We want to package up sort of a little development kit based on our base firmware. We create our own API, maybe include some of Zephyr APIs, and now we want to pass along not our whole firmware, not our whole firmware source, but just a little part of it, a little, a box of headers, CMake files, and so on that we can give to somebody else, and they can build extensions for themselves that we can load. So that's exactly what this PR does. It adds some great tooling to do exactly that. Yeah, so what are some use cases for today, maybe tomorrow? I think many of these are kind of hopefully clear, but we can use them for plugins. So if we have firmware that does audio, video, or sensing processing, we can create plugins to our pipeline of processing steps. We can also create isolated and updatable processes. So if we have a device and we want to be able to run multiple pieces of firmware on that single device, but have different sort of sandboxes that each one can play in. We can do that. We can create multi-tenant firmware based on a based image with the EDK involved. Quite nice. Potentially, we can also have sort of a base firmware with all our drivers, with all of our logging, everything sort of there, and we want to reload quickly. We could potentially, keep, let's say, 90% of the firmware, running in memory, and unload and load sort of a main loop that's nice and small. If we look at Arduino and their sketches, I imagine that's quite a useful case. And perhaps drivers. If we kind of look at how Linux kernel works with Linux kernel modules, there's possibly a use case here to load and unload drivers in cases where your hardware might vary. Maybe we can keep a lot of our code, some of our larger drivers on flash, and load them in memory as needed depending on the board configuration. So, right, what are some caveats? I mean, this is relatively new. There's no built-in signing mechanism today, so you can load any code that you build. There's no restriction on it today. That's sort of left up to you. It's a framework to build on top of. Debugging is an interesting story. I mean, you can debug at an assembly level. For Hello World, that's pretty straightforward. You're looking at a small little page of assembly. Otherwise, you do need to kind of load the symbols, and that can be a bit cumbersome. As noted, before, if you have sort of kernel objects, with this can be a little bit tricky as well, because some kernel objects, especially when you enable user space, want to live in a particular location in your memory at build time. That's used for perfect hash function. So when you pass your kernel object in through a syscall, it effectively uses the address of that and throws it into a perfect hash function to verify things. That doesn't exist if you try to statically declare, say, a mutex or a semaphore in your extension, and then go ahead and use user space with it. It's not gonna, it's gonna fail in a fun and not so fun way. Lastly, I mean, there's a couple other things, right? Dictionary logging is kind of a, how do we do this? Today, not a great answer, so some missing puzzle pieces there. Execute in place is not supported today. As you saw, we need to load all these things into memory to apply these relocation instructions that are associated with each section. That means we have to manipulate all of that stuff in read-write memory and RAM. And probably one of the things that I really kind of look forward to, or I'm trying to work on probably next is at least having some stability in terms of ABI and syscall guarantees. Each time we build today, the syscall IDs change. So if you did want to use user space with this and solely user space with this, you have to be pretty careful not to change your base firmware build where it will change the syscall IDs. It would be nice if those syscall IDs remain the same. Going a step further, kind of creating an ABI would be quite nice. So you could load firmware, you could update your base firmware and keep your extensions the same without having to rebuild them necessarily. So I do kind of want to point out that this was not solely me. This was quite a few people over time making this, and I think that's a real testament to open source. Prior to me, there was a PR for an ELF loader by a former Intel employee. Luca at Arduino added a lot of great RMV7 and CMake tooling. One of my colleagues in the Sound Open Firmware project added extensive support and dynamic shared ELF linking support with PLCs and global offset tables and things of that nature. Cedric and Benjamin has a great, I don't know if Benjamin's in the crowd, but if you look on LinkedIn and you search for LLEXT and Zephyr, you'll see an awesome demo by Benjamin Cabe with LVGL involved, where it loads and unloads various GUI modules. It's really quite something. So, and I kind of just glued it all together, to be honest. So That's my talk. Thank you very much. If you have any questions, I'm happy to answer them.
I'm working with a. So it's working. I'm working with the Sound Open Firmware project, and we have proprietary libraries. Is there any preprocessing that you need to do on the ELF, or do you need to have it compiled with certain flags?
So yeah, kind of going back to the relocations, right, that are there. Not all relocations are supported for all architectures. Basically, ARM is the only one today that I believe supports all relocations, and that's again thanks to Cedric from Schneider. I believe Giannotti from SOF has added many of the Extensa relocations because hi Daniel, I'm assuming you're talking about Extensa in this case, correct? Yeah, so I mean, I assume that many of the Extensa relocations are possible and already implemented, but if not, then that's something that would need to be done to support that. But really, that's kind of the biggest barrier is supporting those relocations.
Hi, fantastic talk, thank you. Question about the architecture support. I guess that right now it's Cortex-M plus Extensa or anything else? Yeah,
that's right, yeah. So there is like an architecture hook today. I think it's probably, it will probably need to be refined somewhat as time goes on, depending on like what kind of parameters need to go in there. But yeah, today it's Cortex-M and Extensa.
All right. And for the build process, because you mentioned that there is a PR with the let's say SDK, what? EDK, sorry. So do you build your extensions against your application so that all the memory limitations are taken into account, or do you build it separately? What's the process?
Yeah, so it depends on the route you want to go. So if you can use the built-in like CMake functionality, right? If you have your base for, you have your Zephyr application, you could use that to build extensions right in line, right next to your application. If you want to build outside of your main applications, that's exactly what Ederson's development kit, or extension development kit is there for, to do exactly that. You can effectively, there's a new target added to the CMake target list, right? In your base application, you build the LLEXT EDK. It generates, I believe, a directory, right? Or maybe a tarball. One of those. Yeah, effectively some sort of like directory or tarball that you can basically package up and give out, and that's all you would need then at that point to go and build. Besides the compiler tool chain and such, right? But that's all you would need to go and build an extension at that point. It includes all the headers, CMake, compiler flags, and so on. Yeah.
So yeah, what are the thoughts on like ecosystem directions for like complicated dependencies? I'm thinking about things that want to link to like libc++ and libraries going on and on and on, often with transitive dependencies. Like obviously, one could force apps to sit there and make a static library out of everything they're going to depend on. Is there hope to handle some of this in a kind of like the HAL directory that we have right now? Something where there's like a repository of like pre-done integrations.
Yeah, I mean possibly. Like there's no real limit on it today in terms of. So I don't know if I said this, but extensions, I believe today can depend on other extensions. If it's not today, that is a planned feature by others and myself. So you could have, like kind of the equivalent of a shared library. So if you kind of have that going on, right? Like I think Cedric, you were talking about CanOpen, which is quite large, or maybe you have a library of plugins for your particular firmware. Maybe it's audio, maybe it's sensing, maybe it's imaging, right? Image processing. I think that would be great. I think that's sort of outside of the scope of Zephyr mostly, right? I mean, that's sort of application dependent and how your embedded application wants to work. But I mean, certainly that's possible.
In terms of relocations, I know it's not a complete solution, but could position independent executables help the situation?
They probably could. Yeah, I haven't looked too deeply into those. So, I understand that, yes, they can. There's sort of a cost, out of that, as I understand it, though, because you have to, pay like a register cost to keep around like what position you're in. You have to sort of load things in a particular place. Then, as I understand it, I'm not, I haven't looked too deeply into this. So tell me if I'm wrong, but. Yeah, so I believe there's some cost to that. And that's sort of true, I don't know if I said this as well, but that's sort of true depending on how you do ELF linkage as well. So if you do relocatable ELFs, you sort of get like the best possible outcome potentially in terms of instruction like size and speed, because you're not doing additional loads and stores for like, hey, I need the address to print K. Well, I mean, as you saw, there was a separate address right in the text section. It had to go load that, then call to it. If you were to do if you were to just build this normally, it'd be a single instruction, a BL, here's the address, PC relative, go jump there, right?
Yep. Second question is around execute in place support. Does it sound reasonable to do the relocation at the time you're saving the extension to the flash?
Yeah, I mean, I think it's quite possible. You could, if you knew, I think like anything is possible, of course, right? But the way it is today, it's all very much dynamic. But you could possibly have like fixed slots, so you do like relocation for everything ahead of time, knowing that you're going to load that particular extension in a particular place in memory. But that's sort of the problem, right? You have to know where everything's going to be ahead of time to do those relocations in Flash. Potentially, I had thought about, maybe you could basically go, this is costly, right? But maybe you could do it where you read in your ELF, knowing where you're going to put it, rewrite it in Flash, saving it back, only loading the read-write portions, and then execute from Flash still, potentially saving like the text section, right, and the read-only data section. You still have to pay the cost of the data, though. So, I mean, there's some options. Yeah.
In Zephyr, I understand the build is application-driven, which means I take my application and build a single binary with everything.
Yes.
And this doesn't really play well with our current build system and our workflow. I was wondering if this could potentially become a way to disaggregate and decouple my application and drivers from, a binary that encapsulates all the Zephyr kernel and other things. Or am I taking it too far?
Yeah, I mean, I think that's like a different problem. Unless you're talking about, you want to segregate your application into things that you want to load and unload at runtime. I think building, these things as like separate libraries that then link together at the end is a separate issue, if that makes sense. Yeah.
Thank you.
Well, on the point about setting the addresses when you flash the app, you actually have a two-way problem, right? Because if you had something on the slide there about the different user domains, I guess, or usage domains. So one of them that you want to be able to update independently is it would be like the host kernel OS, right? And so those addresses may change too.
They might.
But I think what's interesting to think about though is on some of the various like loadable libraries that you see in Linux and things like that they'll have approaches where you can at load time they might update all the addresses, or at runtime they have that special little thing. They jump off to a little function, they figure out what the address is, updates it. The second time you go through the function or the thing, it doesn't have to do that because it's already patched it or whatever. So those are like all these little interesting little tricks to consider. But I think you have to deal with the fact that once you have these loadable modules, you're going to be in a situation where you also want to be able to load anything in there and be able to fix up any of the addresses.
I think you're right. Yeah, and it could be like, again, it's a framework or a toolkit to build on top of or change to suit your particular needs, right? I work at Intel, so you know I've tried to focus on Intel problems in this, and that's you know I'm very happy to see outside contributors because it does sort of expand the use case. But absolutely, yeah. I mean, there's going to be some fun things you can do and some very tricky things you can do regarding this, right? Yeah.
So great talk. This stuff is really cool. There's a couple of questions with the extensibility, and you know, you keep describing it as a framework from a security perspective. So I guess the first question is, like, with code signing, is it possible to patch in some sort of function where you verify before you allow the load to proceed, and then following the load finishing and the patching of every address, is it possible to have a function that you hook in afterwards to do something like reconfigure your MPU to now make that region and RAM execute only? You know, you can't modify it.
Yeah. So I mean, really, you're entirely in control of the flow of things. So there's a function to load, but that's something that your application can call in any context it wants, right? There's a sample, the shell loader, where you can dump in a hex dump of one of these ELFs, and it'll load, and you can then call out to a symbol. But that there's nothing that says that's the only flow that's there. You can absolutely check. Maybe you prefix or suffix your ELF file with an HMAC signature of some kind, right? And you go verify, hey, this is all signed by a trusted key that I know, I trust it, before even trying to decode that it's an ELF file. That's totally doable. And nothing actually, today at least, nothing actually runs when you load. So the only thing that happens is, we interpret the ELF file, we copy data, we do the relocations, and we provide a symbol table that your application can then find a symbol in there and call into. So if you have a particular use case where you want all of your modules to have an entry point, that's entirely up to you. You could absolutely do that. Maybe you had a macro like my cool firmware in it, right? I mean, Linux has this already sort of built into modules, but that's a particular use case for kernel modules. This is sort of like more of a toolkit in terms of like what Linux kernel modules would use, or even Linux user applications and shared libraries would use. So it's sort of the base of all of that. Yeah.
You mentioned that part of this of LEXT is kind of memory management and so forth. Can you speak a little bit more to kind of what the configuration there is for someone using this on, like, carving out memory for the loadable modules and so forth?
Yeah, absolutely. So, I mean, today there's and it is a very simple model today. There's a single heap, right? So there's a config. It's a dedicated heap to LEXT, but there's a single heap. You set the size in kilobytes, and it is kilobytes because, as soon as you talk about enabling the MPU or MMU, you're going to use some space just simply for, as in the last talk, if you were here for that, there's going to be padding for pages or MPU alignment. So it does need to be somewhat sized to account for the various sections that are going to need to be allocated there. But in effect, yeah, there's a single heap. There's also an option, and the Sound Open firmware does use this, where not all memory has to be allocated. So you don't have to allocate all sections from the extension. If you know that your extension already lives in some addressable memory that you can already do these sorts of like permission setting bits and so on. Yeah.
All right, I'm going to ask you about CHRE.
Yeah.
Android's Context Hub runtime environment, and how that differs from the solution.
Yeah, absolutely. So, in fact, just to clarify, like some sources of inspiration that I took for this, one of them was CHRE. I did look at that. I looked at Linux kernel modules. I looked at quite a few things. I looked at some linkers because it turns out, you need to actually do linking as well. But CHRE does kind of a subset of what this does. So it has a fixed symbol table for that. So CHRE is a sort of a subset of what this does, right? There's a fixed symbol table that it provides to I think it's nano apps in this case, right? But in effect, it's kind of doing all of the same things. It doesn't do necessarily the memory bit permission setting that I believe. You can double check that, Keith, if you want. I don't believe it does, but Otherwise, yeah, it kind of does the same song and dance in a lot of ways, but in a very specific way.
Hey, thanks for your talk. I'm actually giving a talk on WebAssembly later today, and there's a good amount of differences between what you're doing there and the extension models here. But I was curious if you looked into that at all, and what you see as some of like the pros and cons versus the different approaches.
Yeah, absolutely. I had someone ask me exactly about WebAssembly and using this. So it was kind of an interesting. So they were using both this loadable module and WebAssembly, and we kind of talked a bit about what were the downsides of WebAssembly in this case. I mean the main con that's sort of kept that's replaying in my mind is that you don't necessarily have, at least as I understood it today, all the hardware acceleration extensions, or even necessarily all of the kind of one-to-one hardware instruction mapping, right? So I mean, there's part of that, but there's also there's some overhead, and you have effectively a runtime. This has no runtime. This is you're building for that target. It's and it won't run. WebAssembly has I would say that the one benefit of being portable across architectures. This is not. You're building for this architecture. You can use all the instructions available to you, all the hardware acceleration available to you.
You mentioned kind of how we have this export symbol. Is there something like, are kernel symbols exported by default, or do we have to go change everything, or kind of?
Yeah, so I mean, so far export symbol has been added sort of as needed by tests and users. Part of that EDK PR, or actually that was a previous PR, I believe, right, Ederson, where Ederson went and added as part of, so anytime I believe the syscall macro is there, it's already exported for you. So a large number of Zephyr APIs are already exported. I believe Giannotti added a lot of the libc symbols, so you don't necessarily have to statically compile your libc along with your extension. You can use the base firmware's libc functionality. But yeah, it sort of comes as needed basis. There's possibilities, so I didn't really talk about that either, but there's the possibility that maybe you want to limit what symbols are available to an extension, and there is that possibility to go manipulate that part of your ELF file at some point in your build step, right, where I only want to supply like a subset of functionality to extensions to be more in line with a plugin type system. But yeah, today it's sort of as needed, and if you need more, feel free to send a PR or just add them to your application. So yeah.
Any more questions for Tom? Oh, yeah, there's one.
I think in your presentation you said maybe drivers, question marks.
Yes, yes. So that, yeah, I'm glad you're asking about that. I mean,
yeah, I just thought, did you already look at the DTS problem? Because the DTS, you have all your hardware. So now if you want to add drivers dynamically, maybe you won't be in the DTS. So did you already look at that, or?
Yeah, so that, I mean, I haven't looked at it too deep, and that's kind of why there's a question mark there. But I think, like, again, we go back a couple talks, right? Ederson has a great talk about deferred initialization, and I think there's a possibility there to sort of combine extensions and deferred initialization to be a little more than just, hey, don't run my init function right away, but possibly, when you run your init function, maybe that goes off somewhere and loads a module possibly. But no, I haven't looked too deeply at it. It's something that I'd happily accept a PR for if anyone's interested.
Yeah, sure.
All right. Anything more? All right. Thanks a lot, Tom.
Yep.
Great talk.
Absolutely. Thank you.